Good morning, folks. This is Mike coming back at you with another video on Foundations of Math 2. In the previous video, we got ourselves a little bit of an introduction into the world of probability. We gained some familiarity with some terminology, and then we saw the difference between empirical and theoretical probability. In this video, we are going to continue our discussion on things related to probability. More specifically, we're going to talk about ways that we can calculate the number of outcomes in a sample space, which, as we know from our previous video, is a critical piece of determining probabilities. But one of the most important things we need to do in any situation whatsoever where we want to calculate a probability is we need to either determine all the possible outcomes, or at the very least determine the number of all possible outcomes that there can be for a probability experiment. In some cases, it's nicer to actually, or I shouldn't necessarily say nicer, but it's not that bad to write out all possible outcomes. But in some cases, it's way too long, way too tedious, way too time-consuming to actually write out every single possible outcome. So we're only concerned really about the number of possible outcomes that there are. And that's what we're going to talk about in this video. We're going to talk about some methods and some formulas we can use to do this. If there's not a ton of possible outcomes for your probability experiment, you can actually visualize all the possible outcomes. And one way you can do that is with a tree diagram. So suppose you toss a fair coin 3 times. We've created a tree diagram here to show all the possible outcomes. This is the tree diagram right here. We see this is our first flip. You can either get heads or tails. Now we go on to our second flip. That's the second column of heads or tails that we have here. So you can flip heads again after flipping a heads, or you can flip a tails after you flip a heads. And you could, after flipping a tails, you could flip a heads, or you could flip one more tails. And now we have our third flip. After flipping 2 heads, you could flip a heads or a tails. After flipping a heads and then a tails, you could again go heads or tails. And similarly with this section down here, you could go tails, heads, heads, tails, heads, tails, 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 heads, or tails, tails, tails. So this is a nice visual as to how you can see all the possible outcomes of this probability experiment of tossing a fair coin 3 times. How many possible outcomes are there, though? Well, to figure out how many, you just follow the trail of marks here. So heads, 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 that's 1. Heads, heads, tails, that's another one. So we're at 2. Heads, tails, heads makes it 3. Heads, tails, tails makes it 4. And then 5, 6, 7, and 8. So we know that there are 8 possible outcomes. And you could do the same kind of thing with any similar kind of probability experiment. You obviously want to do this with something where there's not a ton of possible outcomes, and you're not doing this with a ton of trials. You could do this where you, say, roll a fair 6-sided die once, and you roll it twice, and you figure out what are all the possible outcomes you can have. That's a little bit nastier, but overall still not that bad. But if you were going to roll, say, a 10-sided die, and you're going to roll it 10 times, you don't want 10 columns of values for 1 through 10, and then for each of those possibilities, 1 through 10. It's just way too long, way too time consuming. And it would just be a massive pain to have to actually write out. So tree diagrams do have their uses in nicer situations, but we don't always have those nice situations. We don't always have something where we can just draw a tree diagram and visualize all of the outcomes that we'll have. So how do we do that, or how do we sort of accomplish the same task of figuring out the number of possible outcomes in our sample space when we don't have a nice situation like this? So as I just said, in many cases, though, there's too many options and or trials going on, and a tree diagram just isn't practical. Thus, we use something called the fundamental counting principle to determine the number of possible outcomes for a sample space. In a sequence of n trials, if the first trial can happen k1 or k sub 1 ways, and the second can happen k sub 2 ways, the third trial can happen k sub 3 ways, so on and so forth, all the way through the nth trial can happen k sub n ways, then the number of possible ways that this sequence of n trials can happen is simply the product of these k values. k1 times k2 times k3 times kn. And maybe that just on the surface doesn't seem very clear, but we'll go through some sample problems in detail to hopefully clear that up and hopefully make you see, oh yeah, that does make sense. So, first up, how many 7-digit phone numbers can there be in an area that has one area code? So I'm going to draw some lines here. Obviously, all phone numbers in the US, you have your 3-digit area code, and then you have your 7-digit phone number. So within an area code, in theory, how many different 7-digit phone numbers could we have? Okay. Well, obviously we have the numbers 0 through 9. It's certainly possible to have any of those numbers as a digit in your 7-digit phone number. So if I look at the first number here, or the first blank here, I should say, what are the possibilities for the numbers we can have there? Well, we could have 0, we could have 1, 2, 3, 4, 5, 6, 7, 8, or 9. In other words, we could have 10 different numbers there as a possibility. Okay, moving on to the second blank here. With phone numbers, it's very possible that you have digits that repeat. So we don't have to worry about the case where we can't have the same number happening more than once. So how many numbers could we have here? Well, again, 0 through 9, or 10 possibilities for what can go in that second blank there. The first trial here, or the number that's in the first blank here, can be one of 10 different numbers. Same for the second, and it's going to be the same for all the other ones. We can have any of the numbers 0 through 9 in any of these spots here. We could have all zeros, all fours, all eights. Most phone numbers we know, they aren't like that, but still, we could have that. So, using the fundamental counting principle, the number of possible 7-digit phone numbers that we can have inside of an area that only has one area code is going to be the product of all these 10s. It's going to be 10 times 10 times 10, or 10 to the 7th. And if you do, in your calculator, 10 to the 7th power, you are going to get 10 million. So you can have 10 million different phone numbers all within the same area code. Given that our country's population is certainly less than even 1 billion, we're nowhere near that. And if you think of how many counties we have in each state in this whole country, having 10 million possible phone numbers per county is most certainly a very large number of phone numbers for us to possibly have. Realistically, we don't really have to worry about getting anywhere near that. But this is our first sample problem here on using the fundamental counting principle. Maybe this problem gave us a little bit more of an understanding as to the reasoning behind this principle and how it works. But let's go on to another problem here. Suppose you're shopping for a brand new TV. There are 7 different TV brands that you can choose from, and each brand offers their TV in 8 different sizes. Also, when you purchase your TV, you can pick one of 3 special plans for the TV. So how many different ways can you choose a TV brand, size, and then a special plan? So we have 3 things here. We have the brand, we have the size, we have the plan. Well, we said there are 7 different TV brands. Each one of the brands offers their TV in 8 different sizes. And then we have 3 separate or 3 different special plans, and you can pick one of them. So again, how many different ways can you choose a TV brand, size, and plan? You can pick one of the 7 brands, one of the 8 TV sizes, and one of the 3 special TV plans. So it's going to be 7 times 8 times 3, which is 56 times 3, which is going to be 168. So there's 168 different ways to choose a TV brand, size, and plan. So this is a pretty realistic sample question here. You know, anytime you go TV shopping, there are several different TV brands that you have, and you have the varying sizes, and then they, when you go to pay for the TV, they offer the plans, and maybe you want to pick up some kind of plan. So this is a pretty realistic problem here, and this is why it can be so hard to find a new TV, because you have all these possibilities that you can choose from. So that was the fundamental counting principle. This is one technique we can use to determine all of the possible outcomes in a sample space. Before we discuss the next couple of ways that we can determine all possible outcomes for a sample space, we need to introduce some notation and introduce some terminology. Namely, we need to talk about factorials. For any natural number n, and then we have n with an exclamation point after it, that is equal to n times n minus 1 times n minus 2 times n minus 3 times 3 times 2 times 1. In other words, n with the exclamation point after it, and this is read as n factorial. It is the product of all natural numbers less than or equal to n. So 4 factorial would be 4 times 3 times 2 times 1. 20 factorial would be 20 times 19 times 18 times 17 times 16 times 5 times 4 times 3 times 2 times 1. And these numbers do get very, very large very, very quick. An interesting note, you would think that 0 factorial, despite our definition that we have to have a natural number, and 0 is not a natural number, you would think that 0 factorial would be 0. It's not. 0 factorial is 1. In mathematics, there's several instances where we have values for things and those values just don't seem to make sense. It's kind of a paradox, sort of, as to why these things are what they are. And that's just on first sight of it, and just sort of at base level, it's like, wait a second, that makes no sense. There actually is a valid argument as to why 0 factorial is 1. Unfortunately, that sort of proof, if you will, and that valid argument is not really within the scope of this course. We're not going deep into factorials and we're not going super deep into factorials and the theory of factorials and why they are what they are. All you need to know is that 0 factorial is equal to 1. But just as a few sample problems here, just finding some factorials and some quotients of factorials as well. So first up, 10 factorial. 10 times 9 times 8 times 3 times 2 times 1. And in your calculator, you can do 10 times 9 times 8 times 7 times all that stuff. And when you do that, you get 3,628,800. So that's just very basic, just calculate a quick factorial. 5 factorial over 3 factorial. If we write this out as the product of numbers, we're going to find that some things actually cancel out pretty nicely. 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. That's a 1 there. And now looking at the top and bottom, we see that we have the common factor of 3, so we can cancel that out. We have the common factor of 2 that we can cancel out. And then we have the common factor of 1 that we can cancel out. So all this really is just 5 times 4. And we know that 5 times 4 is equal to 20. So I'm going to give you guys a little bit of a challenge, on this third one here. Try to figure out what 8 factorial divided by 6 factorial is. Try to figure it out by writing each thing out as a product of numbers and then canceling. If you're having trouble with it, though, you can do 8 factorial and 6 factorial in your calculator, and then just take the quotient of those two things. But try to do it by writing out the product of the numbers and then canceling out factors. So pause the video here. Once you think you have it, press play, and we'll see if you are correct. All right, let's see if you came up with the answer that you should have. 8 factorial. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 6 factorial. 6 times 5 times 4 times 3 times 2 times 1. And we have a whole bunch of factors there then that can cancel out. 6s, 5s, 4s, 3s, 2s, and 1s. We're only left with 8 times 7, and 8 times 7 is equal to 56. So hopefully you came up with the answer of 56 for that guy there. So we're going to use those factorials now to assist us with a calculation known as a permutation. And we can use permutations to find all possible outcomes of a sample space in some circumstances. But first, what is a permutation? A permutation of objects is simply an arrangement of n distinct objects in a specific order. And I'm going to emphasize here that with permutations, the order does matter. In the next section, we're going to talk about a similar calculation, but with that calculation, the order in which the terms are placed does not matter. So permutations, the order in which they're placed does matter. To kick it off, if you're going to take a permutation of n distinct objects in a specific order, and you're going to use all of those objects, the number of permutations of n distinct objects using all of them is simply n factorial. And we're going to go through some sample problems here and see sort of why that is what that is. First problem here, 5 people are to be sat next to each other on a stage. How many possible orders can we place these 5 people? So here are my 5 chairs. Let's sort of see why this is a factorial. So first chair. I haven't used anybody. There are 5 people, so I have 5 choices of whom I can put there. Okay, next chair. There were 5 people total. 1 person has already sat in chair 1, so now there's 4 options that I have. There's 4 people that can sit in chair number 2. All right, third chair. 5 people to start. We have someone in chair 1. We have someone in chair 2. So there's 3 options as to who can sit in chair 3. Chair number 4. 3 people are already sat. There are 5 people to start. So 2 options as to who can sit in chair 4. And then last chair, everybody else has been sat. So there's only 1 person here that can sit in the last chair. It's the only person that's left. So the number of possible outcomes is going to be the product of these. 5 times 4 times 3 times 2 times 1. And this is, by definition, 5 factorial. And for the record, 5 factorial is 120. So there's 120 different ways that 5 people can be sat next to each other on a stage. Another sample problem here, perhaps a bit more appealing to some of us, hoping to purchase that magical lottery ticket and win millions and millions and millions of dollars and not have to work ever again in our lives. Suppose that a lottery uses 10 numbers and all 10 numbers are drawn. They're not thrown back in. How many ways can the 10 numbers be picked? So, 10. So there are our 10 blanks for the 10 lottery numbers. All right, first pick. You can have any one of your 10 possible numbers there. That ball gets set off to the side. It doesn't go back in. Next draw. How many possible numbers can we pick? Well, we had 10 to start. One number is set off to the side. So for the second pick, we have 9 possibilities, 9 possible different numbers. All right, that ball gets set off to the side. There's now 8 balls left in the box or whatever that you can pick one from. You do your third pick, one of 8 possible numbers. And you can see that we're going to continue in this same fashion. As we pick a ball out and we set it off to the side, there's one less possible number in there for the next draw or for the next trial. So the number of possible outcomes for drawing these 10 numbers is going to be 10 factorial, which from our previous sample problem here, we saw that 10 factorial was 3,628,800. So, in order to win this lottery, you would have to get all 10 numbers in the correct order, or I should say in the same order in which they were picked. You would have to choose the ordering of these 10 numbers so that they're picked in the same way. For all, or for most lotteries out there, like the Mega Millions, the Powerball, all that stuff, there are a lot more numbers that we use, but we also don't care about the order that they are picked in. We just care that we have all the numbers on our ticket as ones that were chosen. So a significant difference between this lottery problem here and what happens in the big wide world of lotteries. We don't care about the order in which the numbers are chosen, and we're not picking all of the numbers that are possibilities. Next, we're going to sort of touch on one of those two things. We are going to touch on the aspect of it where we don't pick all of the numbers that we have. In the next section, we're going to talk on that whole thing where the order in which we pick the numbers doesn't matter. So that nicely leads us into the fact that we don't have to use all of the objects in our permutation, though. The arrangement of n objects in a specific order, so again, order matters, but we're using r objects at a time without replacement. We don't put these things back in, is going to be, now this is NPR. N is the number of objects you have, R is how many you're going to choose, so NPR is going to be n factorial divided by n minus r factorial. So going back to our sample problem where we had the lottery with 10 numbers, so suppose we only wanted to pick 6 of the 10 there. How many ways can we pick and list 6 of the 10 values there? So for that one, it's going to be 10p6. The order matters, so we're doing a permutation. We had 10 objects. We only want to pick 6 of them. So it's going to be 10 factorial, that's our n, divided by 10 minus 6 factorial. Our R value is how many objects we're picking at a time. So 10 minus 6, or 4. 10 factorial divided by 4 factorial. And what you can do is, if you go into your calculator, or you can write out all the factors and cancel out, but you can do 10 factorial divided by 4 factorial. And if you plug this into your calculator, you will come up with 151,200. And once again, you could take 10 factorial and write it as 10 times 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1. And you could also take 4 factorial and write that as 4 times 3 times 2 times 1. And then cancel out common factors and then just multiply together the numbers that you have left over. So that's how many ways we can pick 6 of the 10 numbers. How many ways could we pick and list 6 numbers out of 50 numbers? This is going to get significantly larger. I can promise you that much right now. This one is going to be 50p6. 50 possible numbers that we can pick from, and we're picking 6 of them. This is going to be 50 factorial divided by 50 minus 6 factorial. So this is going to be 50 factorial divided by 44 factorial. And if you plug this into your calculator, you are going to come up with a very, very, very large number. You are going to come up with 1.144 approximately times 10 raised to the 10th. So massive, massive number of possibilities. What this number is actually equal to right here is actually 50 times 49 times 48 times 47 times 46 times 45. And that number there is a very, very, very large number. So you can start to get a sense of why it's so darn impossible to win the lottery, or it's highly, highly improbable. Now, this here is a bit more realistic because many lotteries, they do have a larger selection of numbers that can be picked. They can go from 1 to 50 or even 1 to 60 sometimes. And 6 numbers can be a good number of numbers that are chosen. But again, the order in which we put these things, the order doesn't matter. So is this exactly perfect? Not necessarily, but it's closer to what an actual lottery looks like. And then there's one last possibility we can have for determining the possible outcomes for a sample space. Sometimes we pick objects in an order, but within all the objects, you can take objects and put them into certain groups, say. or maybe some of the objects are identical to each other. So if you have a total group of n objects, and K1 objects are the same, and K2 objects are the same, and K3 objects are the same, and however many groups all the way up to and including KP objects are all the same. And if you add up these groups, add up the number of things in each group, you get your total number of objects, n. Then the number of permutations of these n objects is going to be n factorial divided by k1 factorial times k2 factorial times k3 factorial times kp factorial. So here's a sample problem to show you what the heck we're talking about. Suppose there are 15 marbles in a box, 5 blue, 5 red, and 5 green. If we pick all 15 marbles out of this box and we don't replace them after we pick them, how many different permutations are there for the choice of 15 marbles? So we have 15, but they're sort of broken up into 3 groups. There's blue, red, and green, each one having 5. So these are like our K1, our K2, and our K3 in the formula that we have written right here. The total number of objects, 15, that's our n. So the number of permutations is going to be 15 factorial divided by 5 factorial times 5 factorial times 5 factorial, because we have 5 of each color. And if you do this calculation, if you do each of these things inside of your calculator, you will come up with 756,756. Again, you could write these factors out, and you could cancel some things out, but it's not really the nicest kind of thing here, because there are some numbers that you have to break down into factors and then cancel those things out. So this one, not as common of a kind of thing that you see. However, it is still fairly common, and it is very handy to know this formula here. I would suggest that any factorials that you have to calculate, you simply go into your calculator and you figure out what each of those guys are, and then do the appropriate calculation. Divide, multiply, whatever. So guys, this concludes our video on tree diagrams, factorials, and permutations. If you have questions or comments, please be sure to reach out to me, guys. Emails, texts, voicemails, paper airplanes, encoded messages, wrapped in a codex, whatever you need to do. Otherwise, until the next video, take it easy, guys.